Hello, Algebra students. Today we're going to be going over the Unit 2 guided practice. This is at the beginning of the unit. And just so go ahead and open to the front of your unit, and we're going to go ahead and get started on that. Everything I write, you should be writing down. And some of the questions I'm going to ask you to try to do on your own, in which case you could pause the video and try it on your own. I'm only going to ask you to try the ones where they're similar to the ones we've already done. So they shouldn't be too difficult, but if you need help, you could always email me. Well, with that said, let's go ahead and get started and get to the first part of this. So the guided practice, you could start on page 1 here. Here it's just talking about some of the stuff we covered. You can go ahead and read that on your own if you want, but some of the stuff we already covered in Unit 1. So if you need to, you could look at that. If not, let's just move along. And we're going to start with this sort of problem right here. And here we have 3 over 4 equals x over 12. So what we're going to learn in this unit is one of the main things is how to solve something like this. Now, whenever you see a fraction and it says equals and then another fraction, this is what we call a proportion. So this is a proportion, and the way we can solve a proportion, a missing part of it, is by cross multiplying. So we could do 3 times 12 and then equals 4 times x. So 4 times x, that's 4x, equals, and then 3 times 12 is 36. Getting x by itself, you would just divide by 4, both sides, and that'll give you that x equals 9. Okay. Now, you might have been able to solve this a different way, and we'll go over that as well. But would you say that 3/4, one thing they want you to see is that 3/4, the original fraction we had, is actually equal to the resultant fraction 9 over 12. These are equivalent fractions. If you checked in your calculator and you divided 3 divided by 4 and 9 divided by 12, you'd get 0.75 for both. So these are actually equal fractions, and that's one way you know you did it right. Now, is this fraction greater than 1/2 or less than 1/2? Well, hopefully you can see that this would be greater than 1/2. So we're going to put greater than here. Greater than 1/2, because 2 out of 4 would be half, right? 2 is half of 4. So 3 out of 4 is more than half. Is there another way we could have solved this one here, finding x? Well, yes, we could say, okay, well, what do I need? This denominator is 4. What do I need to multiply to get to 12? Well, you can multiply by 3, and that'll give you 12. And I multiply the top by 3 to get this numerator. That gives you that x equals 9. So that's another way we could solve it. Okay. This one requires perhaps a little more thought, and it may be tricky if the fractions aren't easy to work with. But we could always use the first method with the cross multiplication. We could always use that method. Now, what they want to point out here is that if you have any fraction, let's say 3/4 in this case, as long as you multiply the top and the bottom by the same number, you will always get an equivalent fraction. So if we multiply, in this case, both top and bottom by 5, you will get 15/20. And this is still equal to 3/4. So it's an equivalent fraction. And here we just multiplied both top and bottom by 5, but we could have multiplied top and bottom by anything and get an equivalent fraction. The next one asks you to multiply top and bottom by 25. So here, 3/4, and we'll multiply both the numerator by 25 and the denominator by 25, and we'll get another equivalent fraction, 75 out of 100. So as long as you multiply both top and bottom by the same number, you will always get an equivalent fraction. Okay. Why don't we try to solve this one here? 12 out of 20 equals x over 100. So there's a few ways we could solve it, but let's just try to solve it with cross multiplying. That's the method I want you to get used to the most because it's more or less foolproof. So 20 times x, again, cross multiplying. 20 times x is 20x equals, and then 12 times 100 is 1200. Divide both sides by 20 to get x by itself. That'll give you that x equals 60. And you could always use your calculator there as well. Okay. Now we could use that idea to help us to find any percentage. In a lot of cases, we already kind of know how to find a percentage from last unit. For example, if I wanted to find 20% of 400, what you could always do is just change that 20% to a decimal by moving the percentage over twice and then multiplying by 400. And they're showing that here. But another way we can solve it is by using proportions. And we're going to kind of go over that more so here. Here also they talk about the 10% trick, which was also covered in last unit, where we can find 10% of 400, which is 40. So 20% will be double that. So that would be 80. So that's the 10% trick that they're trying to see you get there. But we could solve it with a proportion as well. So 20%, whenever you think percent, always think over 100 because percent means for each 100. Cent means 100. That's why there's 100 cents in a dollar or 100 years in a century. So when you hear the word cent, you should think 100. So 20% is the same as saying 20 per 100. Okay, so 20% of 400. And we could use a proportion. So 20% of 400, the 400 is the total. Okay. Now from here, we can cross multiply and divide, same as what we've done before. So 100 times x is 100x. Again, cross multiplying in a proportion equals 20 times 400, which is 8,000. Divide both sides by 100 to get x by itself will give you that x equals 80, which is the same answer we got before. Here, they want you to find 30% of 80 using a proportion. So 30%, that's 30 out of 100. And 80 represents the total that we're taking a percentage of. So that total goes here. Okay. Like 100% is the total, so you put the total in the denominator. And I want to know 30% of 100 is how much out of 80. So we're going to cross multiply. So 100 times x is 100x. 80 times 30. Well, I can just do 8 times 3. That's 24. And then add 2 zeros. So 2400. Divide both sides by 100 to get x by itself. That gives you that x equals 24. So I already know that you know how to find this percentage from the first unit. You could always just change it to a decimal and multiply. But the reason why we're showing this proportion way is that this will become very handy when we're solving different types of percentage problems. And we'll get more into that as we go. Another thing proportions are going to be used for is stuff like with recipes. This is something that's very practical, is when you want to double a recipe or half a recipe. So in this example, it says vegetable soup. This recipe serves 10 people. So we have a recipe that gives 10 servings. But what about if we wanted to do 40 servings, right? What if we wanted to do 60 servings, 30 servings, right? So what would we have to do to find the amount of each ingredient in those situations? Well, we could use a proportion. So we know that this recipe serves 10 people. So in this case, it says how many cups of garlic are needed to make 40 servings of soup. So when we look at the garlic, it takes 1/3 of a cup of garlic for 10 servings. So we say 1/3 of a cup is for 10 servings. But I don't want 10 servings, I want 40 servings. So that's going to go down here, 40. Notice this is the garlic over servings. Here we should have the garlic over servings as well. So I don't know how much that is. But we could easily solve it by cross multiplying. So 10 times x is 10x. And then 40 times 1/3. You could just multiply the 40 times the numerator. So that's 40 over 3. Now to get x by itself, you divide both sides by 10. And you can go ahead and use a calculator. Essentially what you would do is you would do 40 divided by 3 and then divided by 10. Um, 40 divided by 3 divided by 10. So that would give you 1.3 repeating. And if you wanted it as a fraction, that would be 4/3 cups. Okay. How many cups of tomato paste were needed to make 60 servings? So we know the recipe only makes 10 servings, but I want to make 60 servings. Well, how much tomato paste is needed for 10 servings? So for tomato paste, that was 1/4 of a cup for 10 servings. How much for 60 servings? So again, cross multiplying, 10 times x is 10x equals 60 times 1/4. That's the same as 60 over 4. Here, this one's a little bit nicer than the other one because 60 divided by 4, that divides evenly. That gives you 15. So that's 10x equals 15. Divide both sides by 10 to get x by itself. So I'll give you x equals 15 over 10. We could reduce that to 3 over 2, reducing both top and bottom by 5. Okay. How many cups of carrots are needed to make 30 servings? So we know the recipe makes 10 servings, but I want 30 servings in this case, so I want to triple the recipe. So how much carrots are needed for 10 servings? Where's carrots? 1 1/2. 1 1/2, I'll change that to 3/2. That's the same as 1 1/2. Okay, cross multiply. So 10 times x is 10x equals then 30 times 3 over 2. That would make, multiply the 30 times the numerator. So that's 90 over 2. And fortunately, this divides out to 45. So we've got 10x equals 45. Divide both sides by 10 to get x by itself. That would be x equals, and I would reduce both top and bottom, divide both top and bottom by 5, right? In this case, they have a greatest common factor of 5. So that would be 9 over 2. How many cups of onions are needed to make 20 servings? So we know the original recipe produces 10 servings, but I want to produce 20 servings. And we want to know how many cups of onions. Okay, so we would look at onions here. So in this case, 3/4 of a cup. So we would use 3/4 of a cup. cross multiply here. So 10 times x is 10x. And then when we multiply 20 times 3/4, you multiply the 20 times 3. So that's going to be 60/4. In this case, 60 divided by 4, that nicely divides. So that's going to be 60 divided by 4 is 15. Divide both sides by 10 to get x by itself. That would give you x equals, and let's go ahead and reduce this. We could divide both top and bottom by 5, 3/2. How many cups of olive oil are needed to make 5 servings? So this time we're cutting the recipe. We're cutting the recipe in half. So instead of 10 servings, I only want 5 servings. And I want to know how many cups of olive oil. So we'd go to olive oil, half a cup for 10 servings. So half a cup for 10 servings. How many cups for 5 servings? So again, cross multiply. So 10 times x is 10x. Cross multiply. 5 times 1/2 is 5/2. Divide both sides by 10 to get x by itself. X will equal 5/20, which reduces down to 1/4. Right? I could divide both top and bottom by 5 to get 1/4. I know these are kind of tricky. Don't worry, most of them are not this complicated. Just follow along and you'll start to get the hang of it. How many cups of tomato paste are needed to make 5 servings of soup? So again, we are cutting the recipe in half. So originally we had 10 servings for the recipe, but now we only want 5 servings. And I want to know how much tomato paste. So for tomato paste, that would be 1/4 of a cup. 1/4 of a cup for tomato paste. Yeah. But that makes 10 servings. I only want 5 servings, so it's cross multiply. So 10 times x is 10x equals 5 times 1/4. You just multiply the 5 times the numerator, so 5 times the 1. So that's 5/4. Divide both sides by 10 to get x by itself. That cancels the 10. X equals, now when you have a fraction divided by another number, you can actually multiply the 4 and the 10 here and make it 5/40 like this. And that'll actually reduce. We could divide both top and bottom by 5, giving us a reduced fraction of 1/8. Number 7, how many cups of water are needed to make 2 servings of soup? So the original recipe makes 10 servings, but let's say I only wanted to make 2 servings. How much water would we need? So for water, it was 8 cups of water. So 8 cups of water makes 10 servings, but if I only want to make 2 servings, cross multiply here and here. So 10 times x, that's 10x, equals 2 times 8 is 16. Divide both sides by 10 to get x by itself. Gives you that x equals, we could reduce this by 2, so that would be 8/5 cups. Okay. Of course, you could always change all of these fractions into decimals if you want, right? For example, 8/5, if you want to change it to a decimal, you just do 8 divided by 5. That would give you 1.6. Okay, so you should be able to change all these fractions into decimals if you want. Okay, let's look at the next page, page 9. All right, so here we have a box score, which shows the Dodgers hitting statistics for 5 months in the 2009 baseball season. If you look right next to each player's name under the column labeled AVG, you will see that each player's batting average was 5 months into the season. Batting average measures the hitter's performance by determining how many times he successfully hit the ball as compared to the number of times at bat. Okay, so we can see, for example, this first person, they had an average of 0.400, which is really good. And you could see this last person had a batting average of 0.214, and there's everyone in between. Okay. Okay, blah, 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 blah. There's some baseball stuff, blah, 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 blah. Okay, let's go to question 1 here. Andre Ether only had 6 hits in his last 25 at-bats. What is his batting average? So the batting average is always out of 100. So if he got 6 hits out of 25 at-bats, basically we want to find what this value up here would be. So one thing we could do is we could just say, okay, 25 times what gives me 100? Well, 25 times 4 gives you 100. So I'd multiply the top by 4 as well. 6 times 4 is 24. For batting average, they always go to the third decimal place. So that's why it says out of 1,000. So 100 times what gives me 1,000? 100 times 10 gives me 1,000. So I'll multiply the top by 10 as well. So that's 240 out of 1,000. So his batting average, 240 out of 1,000. That's the same fraction as 6 out of 25. Now you should be able to check that with your calculator. Like if you do 6 divided by 25, you should get the same answer as if you did 240 divided by 1,000. It should give you 0.240. So his batting average is 0.240. Okay. Batting average always goes to 3 decimal places, even if it's a 0. Okay. Take a minute to prove that these fractions are equal. So one way to prove that 2 fractions are equal, like I said, is by putting it in the calculator, right? 6 divided by 25, and then 240 divided by 1,000. But another way you could do that is by cross multiplying. So if these fractions are equal, the cross multiplication should also be equal. So for example, if I did 6 times 1,000, that's 6,000. That should be equal to 25 times 240. 25 times 240. And indeed, that also gives you 6,000. Okay, so if the fractions are equal, you could always check by cross multiplying. Well, let's calculate some more people's batting average. So Manny Ramirez here had 12 hits out of 50 at-bats. So that's 12 out of 50 is his fraction here. And we want to make a batting average is out of 1,000. Okay, so this is his proportion that we're going to be solving. What we want to do to solve this is simply cross multiply. So 50 times x is 50x. And then 12 times 1,000 is 12,000. To get x by itself, whenever you see something multiplied by x like this, like 50x, that means these two things are multiplied. So in order to cancel out multiplication, we use division. So we're going to divide by 50. Divide both sides by 50 to get x by itself. So that's 240. Okay, so his batting average, we would say, is 0.240. Okay, so x in this example is 240. So 240 out of 1,000 is 0.240. Now there's a shortcut you could always do here as well. Is simply do 12 divided by 50 and you'll get the same answer. Okay, but here we're just practicing how to do proportional thinking. Okay, so if he got 12 out of 50, how many hits can we expect him to get out of 1,000? Well, we would expect 240 out of 1,000. That's the same as getting 12 out of 50. So this one, I'll help you set it up. This would be 28 out of 100. equals x out of 1,000. See if you could solve this one on your own using cross multiplication. Okay. Then after that, see if you can do this one and this one and this one. Okay. So see if you can do the rest of these on your own. One thing they want you to see is that any number divided by itself is always 1. Okay, so if you have 500 out of 500, that's 1, or 1,000 out of 1,000, that's also 1. Okay, now for this next one, we have this chart about some dietary supplement and how much of each vitamin or mineral it gives you. So you can see vitamin A, it gives you 1,500 mcgs, which is 100% of your daily value. For vitamin C, the amount in the tablet is 60 milligrams, which is 100% of your daily value. And you can see the rest of these as we go down. We're going to be using this to help us with the next set of questions. So here in this problem, it says 8 milligrams is 53% of your daily value, right? That's what it kind of shows here. For zinc, 8 milligrams is 53% of your daily value there. So what would be 100% of your daily value? So we don't have to estimate here. We don't have to do that. What we can do instead is we can simply calculate it. So if 8 milligrams represents 53% of our daily value, then how much would we need for 100% of our daily value? Hopefully you can see you could just cross multiply and solve this, right? So this is the type of problems, this proportional thinking, that this allows us to solve, right? If 8 milligrams is 53%, then how many milligrams is 100%? 8 out of 53 is the same as how many out of 100? So we can cross multiply here. So 8 times 100 and 53 times x. So 53 times x is 53x. 8 times 100 is 800. Divide both sides by 53 to get x by itself. That gives us that x equals, so we do 800 divided by 53, 15.09. Okay, 15.09. Okay, hopefully that makes sense. We already did this. Round to the nearest tenth, if we wanted to do that, round to the nearest tenth, that would be 15.1. By the way, the first decimal place is called the tenths place. So when they say round to the nearest tenth, they're saying round to the nearest first decimal place. So our answer we had before was 15.09. So if we're rounding to this spot, this 9 rounds the 1 up, or rounds the 0 up to a 1. That's why we get to 15.1 when we're rounding to the nearest tenths place. If it says to the nearest hundredth, just so you know, that's 2 decimal places. So you're going to see that sometimes too, where it says round to the nearest tenth, that's 1 decimal place. If it says round to the nearest hundredth, that's 2 decimal places. Let's go ahead and try solving this one here. So we're going to be using that that chart a couple pages ago, but basically it says we're going to be filling this out. So the amount of milligrams in one tablet, the percent daily value, and the 100% daily value is where we solve as a proportion. Okay. All right. So the first one talks about, what are we using? Calcium. So let's go ahead and look at calcium. So 10 milligrams is 1%. Okay, so 10 milligrams here. That represents 1%. So if 10 milligrams is 1%, then how much is needed for 100%? Okay, so if 10 milligrams is 1%, how many milligrams is 100%? So here we cross multiply. 1 times x is just x. Okay, anything times 1 is itself, right? So that includes variables like x. So 1 times x is just x, just like 1 times 5 is just 5. Okay, equals 10 times 100 is 1,000. So you would need 1,000 milligrams for 100% of your daily value. It seems like a lot. Okay, iron. Next one's iron. So let's go and look at our thing. 3 milligrams is 16%. So 3 milligrams is 16%. So 3 milligrams is 16%. So if 3 milligrams represents 16%, then how many milligrams are needed for 100%? So again, cross multiplying gives us that 16x equals 300. Divide both sides by 16 to get x by itself. $18.75. All right. Silesium, folate, silesium, let's see. 15 mcgs, micrograms. I think that's micrograms. 15 mcgs, 71%. Okay. I'll set it up over here. So 50 represents 71% of your daily value. So how much is needed for 100% of your daily value? So I'm going to let you try to solve that one on your own. You see the examples here. Okay. And then try doing this one on your own as well. Okay. So try to finish up this silesium row, finish this up by solving this proportion, and then try doing this one on your own. Okay. Next, we're going to talk about exponents. And I know we talked about it a little bit in the last unit, but basically when you see a number and an exponent, that's saying that's that number times itself that many times. So in this case, it's 5 times itself, just 2 of them. So that gives you 25. Okay, because it's just 5 times 5. Now, I know a lot of people will see 5 to the power of 2 and they'll put 10. Okay, that's not right. That's not right. 5 to the power of 2 does not mean 5 times 2. It means 5 times 5. So that's 25. So for example, another example is 5 to the power of 3. Well, that means 5 times 5 times 5. Okay, so 5 times 5 times 5. That's not 15. That's not 15. 5 times 5 times 5 is 125. Okay, 5 times 5 times 5. That's what this means. 5 to the power of 3 means 5 times 5 times 5, which is 125. So 10 to the power of 1 is just 10. Anything to the power of 1 is itself. Okay, so no matter what the number is, if it's to the power of 1, it's just itself. 10 to the power of 2, well, that means 10 times 10. Well, that's 100, isn't it? 10 to the power of 3, that means 10 times 10 times 10. So that's 1,000. 10 to the power of 4 means 10 times 10 times 10 times 10. So that's 10,000. Right? Notice when it comes to powers of 10, it just adds more zeros. So 10 to the power of 4, there's going to be 4 zeros, for example. 10 to the power of 5 will have 5 zeros. So see if you can do the rest of these on your own. Okay. Next page, page 17. 10 times 100, well, that's the same as saying 10 to the power of 1 times 10 to the power of 2, right? Because 100 is 10 to the power of 2. Well, this would be 1,000. We already know that, right? We already knew that 10 times 100 is 1,000. So 10 to the power of 1 times 10 to the power of 2. Well, this is 10 to the power of 3, right? 1,000 is the same as saying 10 to the power of 3. These are the same. Here, if I was going to multiply 1,000 times 1,000, well, this would be the 1 times 1 is 1. And we're going to put 6 zeros at the end. 1, 2, 3, 4, 5, 6. 1,000 is 10 to the power of 3 times 10 to the power of 3. Well, that's 10 to the power of 6. Isn't this answer 10 to the power of 6? Right? 6 zeros. If I was going to multiply this, this would be 1 with 9 zeros, right? Total zeros. So 9 zeros. 3, 4, 5, 6, 7, 8, 9. Well, 10 to the power of 3, that's 1,000. 10 to the power of 6, that's this 1 million. So that'll give me 10 to the power of 9, which is what this is, 9 zeros. I want you to notice what's happening with the powers. So when I take 10 to the power of 1 times 10 to the power of 2, it gives me 10 to the power of 3. So what am I doing with these powers? Well, hopefully you can see that what I'm doing is adding those powers. 1 plus 2 gives me 3. Here I'm adding these powers. 3 plus 3 gives me 6. 3 plus 6 gives me 9. So when you're multiplying, this is kind of the rule. If I'm multiplying some number, in this case it's tens, but it could be any number. So anything, and I have some power, let's say to the power of 5, and then I'm multiplying, as long as it's the same base, right? So these are both base x, let's say to the power of 6. Then what you would do is you would add those powers. So this would be x to the power of 11, for example. So when I see 2 to the power of 6 times 2 to the power of 10, this would actually be 2 to the power of 16. X to the power of 3 times x to the power of 5, that's x to the power of 8. Y to the power of 4 times y to the power of 5, that's y to the power of 9. Now, it doesn't work in situations like this here. See, because these don't have the same base, right? This one has base 5 and this one has base 8. So you can't say like, oh, that's something to the power of 5. That doesn't work that way. Okay, they have to have the same base, like these examples. Okay, but it should make sense, right? Let's just look at number 5 here as an example. If I had x to the power of 3 times x to the power of 5, well, x to the power of 3, that means x times x times x. And then times x to the power of 5, that's 1, 2, 3, 4, 5. Well, isn't this the same as x to the power of 8, right? That's 8 x's multiplied together. And you can see that there. Hopefully that makes sense. What about when we divide? Well, we know when we divide by 10, we could just take off a 0. So 1,000 divided by 10 is 100. Okay. Well, isn't that 10 to the power of 2? Yeah, 100 is 10 to the power of 2. So 10 to the power of 3 divided by 10 to the power of 1 is 10 to the power of 2. Well, this one here, 1 million divided by 1,000, you can cross off 3 of these zeros. So that gives me 1,000. Well, isn't that 10 to the power of 3? Yeah. So what am I doing with these powers here? So when we're dividing, what do I do with these powers? So 3 and then over the 1 gave me 2. 6 over the 3, that gave me 3. Well, aren't we subtracting these powers? Yeah, we are. We're subtracting the powers. So for number 5 here, so 10 to the power, or 2 to the power of 10 over 2 to the power of 4, we want to subtract those powers. So that'll give me 2 to the power of 6 would be my answer. This one would give us x to the power of 9. Here, 10 to the power of 9 over 10 to the power of 6. Again, subtract the powers. That'll give me 10 to the power of 3. Okay. And I hope that sort of makes sense, right? Let's look at a simple example. Let's say I had maybe we'll use the number 4. 4 to the power of 5 over 4 to the power of 2. Well, 4 to the power of 5 is, well, this would be 4 times 4 times 4 times 4 times 4 over 4 times 4, right? 4 squared. And these cancel, right? So what I would be left with is 3 of these multiplied together. So 4 to the power of 3. So what did I do with these powers? I subtract them, right? 5 minus 2 gives me 3. So let's work on some of these examples. Like I showed here before, if they have the same base like this and they're multiplied together, you add the powers, right? So this would be y to the power of 8. This one, number 2, we'll come back to that. Let's actually go to number 3 next. So these x's have the same base, so we could add those powers. So that's x to the power of 7. And then the y's have the same base, so that's going to be y to the power of 8. What about this one? This one is a power to a power, right? So it says y to the power of 5 to the power of 3. So that's y to the power of 5 to the power of 3. That means there's going to be 3 of these multiplied together. And as we learned up here, well, those you add the powers, right? So that would be y to the power of 15, right? 5 plus 5 plus 5. Is there a shortcut to go from this to that? Well, yes. You would just multiply those powers. So when you see a power to a power, what you want to do is multiply those powers. 5 times 3 is 15. Same idea here. X to the power of 3, this gets an additional power to the 4. So that's going to be x to the power of 12. Power to a power, you multiply those, right? And then y to the power of 8. Again, power to a power. Notice this fourth power is outside the parentheses. That means everything in the parentheses is going to get this fourth power. So that's why it goes both to the x and to the y. Similarly, this squared out here is going to go to the 3 and to the x squared and to the y to the third. So first, 3 squared, that means 3 times 3. So that's 9. And then x squared to the power of 2. Power to a power, we multiply those. So that's x to the fourth. Y to the third squared. So power to a power, multiply those powers. Y to the sixth. Okay. So now we're going to talk a little bit about scientific notation. So scientific notation is used basically to write down very large numbers or also very small numbers. Because a lot of times numbers, when we're dealing with them, especially in scientific areas, we deal with extremely large numbers or extremely small numbers often. So for example, there are this many molecules of water in just one glass of water. So that's 7.5 times 10 to the 23rd. But see how much faster it is to write this, right? So this is scientific notation. Okay, so we can take a large number like this and write it in this form, and that saves us a lot of space, and also makes it so we make fewer errors, because if you leave off a 0, it's very easy to leave off a 0 when you're writing 20 of them. You know, you accidentally put too many or too few. So, for example, 300 is the same as saying 3 times 100, right? So you could rewrite it as 3 times 10 to the power of 2, right? Because 100 is 10 to the power of 2. 6,000 is same as saying 6 times 1,000. So that's same as saying 6 times 10 to the power of 3, right? Because 1,000 is 10 to the power of 3. And this is how we would write it in scientific notation. 6 times 10 to the third. What about this one? Well, this is the same as saying 75,000 is the same as saying 7.5 times 10,000, which is the same as saying 7.5 times 10 to the power of 4. Okay. We could also do the same. Let's go ahead and work on these. And basically the idea, or the kind of the shortcut to writing things in scientific notation, is we just count how many times we're moving the decimal. So in the case of 4,000, if I want to write this in scientific notation, first I need to look at where the decimal is starting. So the decimal is on a whole number, the decimal is at the end. And I want to move the decimal until there's just one whole number in front of it. So here we would move the decimal until only the 4 is in front of it. So how many places did we move it? 1, 2, 3. So however many places you had to move it, that's what's going to go in your denominator, or sorry, in the power of the 10. Similarly, for 84,000, the decimal starts here, and I'm going to move the decimal until there's only one number in front of it. So we have to move it 1, 2, 3, 4 times. So now only the 8's in front of it, right? Now it looks like 8.4. So we had to move it 4 times, so that's times 10 to the 4th. For this one, the decimal is at the end once again. We'd have to move it 1, 2, 3, 4, 5 times. So that's going to be 9.5 times 10 to the power of 5. Now, you could also use scientific notation to write things that are very, very small. So if they have a lot of zeros in front of it. So that's very common also in the scientific world, is you have things with like tons of zeros. And this is actually a very small number, a number close to 0, right? It's 0.000000 something, right? We could write those in scientific notation as well, but instead of having a positive power, these would have a negative exponent on the 10. Okay. So let's go ahead. Let's see, how much more do we have to do? Oh, we still have quite a bit, don't we? Okay, that's all right. We're getting there. So let's start writing some things in scientific notation. So let's start with these big numbers here, and we're going to convert them into scientific notation. So we've kind of already practiced some of these. So the decimals are all at the end for these ones. And we want to move the decimal until there's just one number in front of the decimal. So we're going to have to move it 1, 2, 3, 4, 5 times in this case. So that's going to be 6.25 times 10 to the, we moved it 5 times, so times 10 to the 5. For this one, we'd have to move it 1, 2, 3, 4, 5, 6 times. So we're going to do 2.37 times 10 to the 6. We moved it 6 times, okay? See if you can do 8 and 9 on your own. So I'm going to leave those 2 for you to do. Now, how do we go from scientific notation into standard? Well, the power of the 10 tells you how many places we're going to move the decimal. So in the example of 6.2 times 10 to the 3rd, we're going to move the decimal 3 places to the right. So that's 1, 2, 3. And every empty spot, you're just going to put a 0. So that's 6, 2, 0, 0 in this first one's case. So 6,200. For this one, we would move the decimal 5 places. So if we had 5.8, we're going to move it 5 places. 1, 2, 3, 4, 5. And again, everywhere you see an empty movement, we're going to put a 0 there. So that's going to be 5, 8, 0, 0, 0, 0. So 580,000 in this case. Okay. See if you can do 3, 4, and 7 on your own. Now, what about ones that have a, I'm assuming this one's supposed to have a decimal here. We'll put it right here. What about ones that are really small numbers? So for these, to write these in scientific notation, again, you want to move the decimal so that there's only one whole number in front of the decimal. So in this case, for this one, 0.25. 0.25. We're going to move it just one space. So now there's a 2 in front of the decimal. So since we only moved it one space, we're going to put -1. Now these ones are small numbers. They get negative powers. Okay, so if you had to move the decimal to the right for scientific notation, that's going to give you a negative power. So in this one's case, we'd have to move it 1, 2, 3 places. So it's going to be 3.6 times 10 to the -3. Similarly, for this one, 1, 2, 3, 4 places. So that's going to give you a -4 there. For number 16 here, let's go down to this one. We want to move it until it's behind the 2. So 1, 2, 3, 4, 5, 6, 7, 8 times. Now let's see if we can write these scientific notation numbers in standard form. So here, this one's 9.5 times 10 to the -5. 9.5 times 10 to the -5 means we're going to move the decimal 5 places. 1, 2, 3, 4, 5. Go ahead and put the decimal there. And then any spot that is empty, those get zeros. So it's 0.000095. Okay. Let's do another example. In this one's case, we'd have to move the decimal 6 times to the left. So 7.351. And we're going to move it 6 times to the left. 1, 2, 3, 4, 5, 6. Put the decimal. Each of these empty movements get zeros. So it's 0.000007351. Okay. Try number 15 on your own. Now we're going to talk a little bit about negative exponents. By the way, I want to mention, if you ever need to take a break and come back to this video like, oh, you've been watching for a while, you're going to go do something else, that's fine. You could always watch this video in 2 parts or whatever. Okay. So when you have a negative power, you can rewrite it as a fraction with the positive power in the denominator. So this is just a way that we can manipulate numbers a little bit, which is what algebra is all about. So when we have 10 to the power of -1, that's the same as saying 1 over 10 to the 1. 10 to the power of -2 is the same as saying 1 over 10 to the power of 2, which is 1 over 100, which is 0.01. 10 to the power of -3 is the same as saying 1 over 10 to the third, which is 1 over 1,000, which is 0.001. Can you guess what this one is? 0.0001. So again, whenever you see a negative exponent, you can rewrite it and put it as a positive exponent in the denominator. So let's go ahead and work with that idea. So 2 to the power of -4 is 1 over 2 to the 4th, which is 1 over 2 times 2 times 2 times 2, which is the same as saying 1 over 2 times 2 is 4, times 2 is 8, times 2 is 16. Okay, again, that's 2 times 2 times 2 times 2. See if you can do number 5 on your own. Same thing with variables. X to the power of -2, you can put it as a positive power in the denominator. Here's an example they're showing here. Here, this x has a power to the -2, right? So that one can come into the denominator and change its power to a positive. That's why it's a +2 when it comes down. Okay, so negative powers, once they move where they're at, negative powers become positive powers once they move where they're at. X to the power of 2 and x to the power of 5, you add those powers to get x to the 7th. Remember, if they have the same base and you're multiplying, you add those powers. So for example, this one can be rewritten as y to the power of 4. And we're going to put this x to the power of 3 on the bottom, right? But once it moves, that negative power becomes a positive power. So we have an x to the power of 3, an x to the power of 4, and a y squared on the denominator. We can go ahead and combine those x's. So that's going to be x to the power of 7 down there. We still have a y squared. That does not combine with the x's because these have different bases. And then we have a y to the 4th. Can we reduce these y's? Well, yes. If they have the same base, we can subtract those powers. Hopefully you remember that. So that would be, here you have 4, 2, those subtract. Those give you y to the power of 2 on top, x to the 7th on bottom. For this one, we have a power to a power. So this power gets distributed to both of these powers. So that's going to be x to the power of negative 10. Remember, a power to a power, you multiply those. And then y to the power of 15. Since I don't want I'd rather not have a negative power, we could rewrite that and put this negative power in the denominator. Remember, once it moves down there, it becomes a positive power. The y to the 15 would go on top. When there's no fraction, you can consider these as being on top of a fraction, right? Just like just the number 3 is the same as saying 3 over 1, right? So this 3, you can think of it as being on top of a fraction of 1. So this y to the 15 is already on top, but this x to the negative 10 needs to come to the bottom and become positive. I cannot subtract these powers because they have different bases. Here, let's distribute this. So this would be m to the power of negative 6. Again, a power to a power, we multiply. So that's going to be, and then n to the power of negative 8. In this case, these are both negative powers, so they're both going to come to the bottom. When they come down here, they become positive powers. Right? Once they move where they're at, they change to positive powers. Well, what would be on top now? If there's nothing on top, we could just put a 1 on top, like that. Okay. Let's go to page 24 when you're ready. How many groups of a million are there in 1 trillion? That is, how many times bigger is 10 to the power of 12, 1 trillion, than 10 to the power of 6? So this is the same as saying 10 to the power of 12 divided by 10 to the power of 6. So what should I do with these powers? Well, you would subtract them. So that'd be 10 to the power of 6. 12 minus 6 is 6. Remember, as long as these have the same base, you could subtract the powers in this fraction. So this one would be 10 to the 24 over 10 to the 12. See if you could do this one on your own. Again, subtracting the powers. All right. Now we're going to talk a little bit about like terms. So you may remember from adding or subtracting fractions, fractions need to have the same denominator, right? Like 2/3 plus 1/3, you can add these together because they have the same denominator. Adding or subtracting, they're kind of picky, right? They'll only go when they have the same denominator. But multiplying, they're not picky at all. You can multiply things that don't have the same denominator. So for example, 1/4 times 1/3, you do not need the same denominator here. You just multiply top times top, bottom times the bottom. That's why in a lot of cases, multiplying is easier. But adding is very picky. Same thing when adding or subtracting terms. So for example, I can't add, let's say I had 3x plus 8. I cannot add these together because they are different terms. They are not alike. However, you could multiply them together, right? 3x times 8, they have no problem multiplying. This would be 24x. However, they will not add together. They will only add together if they both have an x, meaning they're like terms. So if they have the same variable, then they can add or subtract. But so if they're just plain 3 plus plain 8, they'll add, or 3x plus 8x, those will add. But if one has an x, the other one doesn't, they will not add. Okay, they're not like terms. But if I'm adding an x, 1x plus another 1x, this is actually 2x. So these are like terms, right? They both have an x. They're both x numbers. And multiplying x times x, well, that's x squared. Okay, x to the power of 2. Here, 2x plus 3x, well, you just add the coefficients, so that's 5x. Again, these are like terms. They want to add together because they are both x numbers. Here, to multiply, we would do 3 times 2, that's 6, and then the x's multiply together too, so that's x squared. So 2x times 3x is 6x squared. The x times x becomes x squared. Can I add these together? Well, yes, they are also like terms. So 5x squareds plus 10 more x squareds would be 15x squareds. Can I multiply these together? Well, yes, multiplying everyone, they could always multiply together. So 5x squared times 10x squared, multiply the coefficients, the 5 times 10, that's 50. And then remember, when we're multiplying x squared times x squared, you add those powers. So that's going to be x to the 4th. Can I add these together? 3x squared plus 4x? Well, no. These do not add together because although they both have x, they have to have the same power as well. Okay, so 4x will not add with 3x squared because this one does not have x squared. This one does. That means they are not like terms. So that's how picky adding and subtracting are. They need to have not only just the same variable, but they also have to have the same power as well in order to be like terms. Can we multiply them together? Yes, of course. Multiplying is not picky. So 3 times 4 is 12. And then x squared times another x, well, that's x to the 3rd. Again, we add the powers when multiplying. What about these? Can I subtract these? No, because these are not like terms. Again, these are not like terms because these have different powers. So in order to add or subtract, they need to have not just the same variable, but also the same exponent. But I can multiply them together, right? In this case, it'd be y to the power of 5 because you add those exponents. Sometimes you might see some stuff, like a bunch of stuff together, and you might be able to combine some of it together, right? So we call that combining like terms. So we might see, okay, I can't add the 5x squared and the 3x to the 3rd. I can't combine these, but I can combine the 5x squared with this plus 10x squared. That'll make 15x squared. So I can combine the terms that are alike. Similarly, the 3x to the 3rd plus the 2x to the 3rd gives me 5x to the 3rd. Can I combine then those together? No, I cannot. So these are not like terms, so I can't combine any further. But you could see we combine some stuff together, but once we get to a point, we won't be able to combine anymore. That's very common that you'll see, oh, some things can combine together and then some things won't be able to anymore. Okay, now let's do some practice. This is all stuff that we've covered before, but I'll continue to go over it. Maybe I'll ask you to do some on your own. So here when we're multiplying, as long as they have the same base, we would add the powers. So this would be 10 to the power of 9. Here, same base being divided, you would subtract these powers. So that's 10 to the power of 3. 9 minus 6 is 3. This would be x to the power of 6. Again, adding the powers. Here, this would be x to the power of what? What do you think? Well, here you'd subtract those powers, so that's 2. Let's go ahead and write these negative exponents as fractions. So this would be 1 over 10 to the power of 1. So remember, once it comes in the denominator, now it's positive power. If I write that as a decimal, that's 0.1. Here, this would be 1 over 10 to the power of 2, or in other words, 1 over 100, right? Because 10 to the power of 2 is 100. So that's 0.01 as a decimal. This one as a fraction is 1 over 10 to the positive 3, which is the same as saying 1 over 1,000. As a decimal, that's 0.001, 1/1000. Now let's write these as scientific notations as standard numbers. So here, this decimal is right here, and we would move it 2 spaces to the left. So 0.03. This one needs to move 3 places. 1, 2, 3. So this is 0.007. 007. Let's go ahead and multiply these together. Again, we multiply the coefficients. So 3 times 5, that's 15. And then x to the power of, well, we would add those powers. Remember, when we're multiplying those, we add those powers. So that's to the power of 5. Here we can add these together because they are like terms. They're both x squareds, right? So this would be 10x squareds. Let's multiply these together. Multiply the coefficients, makes 25. And then x to the power of what? Well, we want to add those powers. So that's to the power of 4. Here, these are both y to the power of 3, so they are like terms, so we can subtract them. So this would be 5, y to the power of 3. Let's multiply them as well. A positive times a negative, well, that's negative. Hopefully you remember that from last unit. And then we add those powers. So that's going to be, well, multiply the coefficients, that's 14. And then y to the power of 6, adding the powers. N squared times n squared times n squared. Well, we would add those powers, so that'd be n to the power of 6. What about if we wanted to add these 3 together? Well, you could think of these as each 1n squared plus another 1n squared plus another 1n squared. So that's 3 n squareds. So when we're adding, we don't increase those powers. Only when they multiply together do we add the powers. Like here, they're multiplying together, you add those powers. Here, if we're adding, don't add the powers. Okay, these are like terms as well, so let's go ahead and combine them together. So 2x squared plus 3x squared, well, that's 5x squared, minus 8x squared, that makes negative 3x squareds. Let's go ahead and multiply these together as well. So multiplying the coefficients, 2 times 3 is 6. 6 times negative 8 is negative 48. And then we have x to what power? What power do you think? Well, we're multiplying, so we want to add those powers. So 2 plus 2 plus 2, that's 6. Let's go ahead and combine like terms here. Well, this 3x squared can combine with what? Well, this 7x squared. These can combine together. So that's going to make 10x squared. And we can combine this 5x to the third plus this 4x to the third, and that makes 9x to the third. Okay. I would actually prefer if we wrote the highest power first. So generally speaking, you want to write your algebraic expressions with the highest power first. Okay, so that's why I'm going to put the x to the third first, and then I'm going to put the x squared after that. Lastly, let's multiply these together. So 3 times 5 is 15. 15 times 7 is 105. And then times 4 is 420. And then we have x to the power of, again, we're multiplying, so we add these powers together. So 2 plus 3 plus 2 plus 3. So that's going to make to the power of 10. Okay, and that's it. All right, I hope that all made sense. I hope you're able to get through it. And if you have any questions, you could always email me. My email is ttrigg@ofy.org. And if you're able to get through all that, hopefully the bookwork won't be too bad. Especially the most important things I want you to understand is a lot of those combining like terms and those exponent rules, and as well as those proportion rules that we covered early on. Okay. Well, with that, I'll see you guys next time when we go over the bookwork. Okay. Take care.